In this section, we are going to discuss how to find maxima and minima values for multivariate functions. So before we jump into the multivariate case, as usual, it's going to be helpful to recall how we did this in the single variable case. So in the single variable case, we identified local maxima and local minima by first finding critical points for the function. The critical points are all points that might be a local maximum or local minimum. Okay? We like to find critical points because it reduces the number of places we have to look. Not all critical points will be local maxima or local minima, but by restricting ourselves to just a few points, it's easier to check just a few points rather than all possible input values. Okay? There are a couple ways we can find critical points. The most common way is we could solve for when the first derivative is equal to 0. When the first derivative was equal to 0, that means we had that horizontal tangent line. Good indication that we might have a local maximum or local minimum, because right at the top of a peak or right at the bottom of a valley, we would have that horizontal tangent line. We'd change from going uphill to going downhill. Or the other possibility is a point where the first derivative is undefined. Okay, it has to be a point on the function, but where the first derivative is undefined. If the first derivative is undefined, something like a cusp or a sharp point, it means the first derivative can't tell us any information about it. We don't have enough information to rule it out as a local maximum or local minimum, so it might be. So we need to include anything where any points in the original function where the first derivative is undefined, where the function is not differentiable. We need to consider those as critical points because they might be a local maximum or local minimum, right? And the critical point should be all the values that could potentially be a local extrema. Okay, once we find those critical points, we need to determine which of them are local maxima, which of them are local minima. So we test them. And we have two tests. The first derivative test and the second derivative test. Okay, first derivative test, you may remember, we constructed a sign chart and we found out before the critical point, are we increasing or decreasing? After the critical point, are we increasing or decreasing? If before the critical point, the first derivative is going uphill, and after the critical point, it's going downhill, that would mean the critical point would be a local maximum, right? Similarly, if we go downhill then uphill, then that critical point would be a local minimum. So that's how the first derivative test works, okay? For the second derivative test, you're looking at the concavity. You plug in the critical point into the second derivative and see if you are concave down or concave up. If you're concave up, you have a local minimum. If you're concave down, it's a local maximum, right? So in the single variable case, we could get something like this. This was our function. We could have a local maximum, right? It's not the absolute highest point in the function, right? There are certainly points that are higher, but it's the highest in its neighborhood, right? Immediately around that point, it is the very highest. Or a local minimum, right? It doesn't have to be the absolute lowest point, but it's the lowest in its neighborhood, immediately around that point. But there are also places where our first derivative might be 0, like this point right here. And let me zoom in so we could really be convinced that the first derivative right here is 0, right at the origin, right? We have a horizontal tangent line, but it is neither a local minimum or a local maximum. It's something else. It's an inflection point, okay? In the multivariable case, we're going to approach this in much the same way. we are going to find critical points. Now, this is going to be where the function is horizontal, but we need to be careful here because now we can't just have one horizontal tangent line because there are lots of directions that we can move in. So we need to make sure that we are horizontal in every direction, not in just one or two directions. Okay? So we need to find our critical points, and then we are going to test those critical points. The way we test the critical point will be similar to how we test it for the second derivative test, but as you'll see, there are a few complications, okay? But the process is largely the same from single variable to multivariable. We just have to be aware of a few extra considerations in the multivariable case. So let me show you what the multivariable case might look like. We could have a function that looks like this, okay? We can definitely see there are some local maxima, okay, some high points. We can see there are some local minima, some low points. What might not be so obvious looking at this particular graph is there is also a place that is in its immediate vicinity, and let me see if I could zoom in without cropping too much of the graph here. In its immediate vicinity, it's flat, right? In this direction, you can kind of see in the cross section be a local minimum. In this direction, you can kind of see in the cross section it's a maximum. And so in every direction, it's horizontal, but it is neither a maximum or a minimum. It's actually a saddle. It's a saddle point, right? In one direction, it's a local minimum. In another direction, it's a local maximum. Okay? So we need to be aware of those two, and we need a way to distinguish between them. So let's talk about how we're going to do these things. How do we find critical points in a multivariable setting? How do we then test those critical points? So let's start with talking about finding critical points. We want to find critical points. We don't want a horizontal tangent line in just one direction, right? We want it in every possible direction, in the x direction, in the y direction, in every other possible direction. Okay? So the idea here is we want the directional derivative in every possible direction u to be equal to 0, right? For every direction u. Now, we know that this directional derivative, let me actually move the 0 to the other side. We know this directional derivative is equal to the gradient of f dotted with a unit vector in the direction of u. Right? The only way that this can be 0 in every single case, in every single direction that you could possibly point in, is if the gradient is equal to 0, right? Because I'm taking the dot product here, and because this can be lots of different things, the only way that it can be 0 in every possible circumstance is if the gradient is equal to 0. So the only way the directional derivative can be 0 in every direction the only way we could get a horizontal tangent line in every direction is if the gradient of the function is equal to 0. So that's going to be how we find our critical points. We need to solve the system of equations where the gradient of f of xy is equal to 0. We need all pairs of xy that make this equation true. Okay? The other possibility is that the gradient of f is undefined at a point. That's certainly possible, and it happens a lot. We aren't going to worry about it too much in this class. Just be aware that it is a possibility here, just like it is in the single variable case. Okay, let's do an example. Let's find the critical points of a function for a particular problem. Let's find all critical points of this function. So as we just learned, we get a critical point of a function when the gradient of the function is equal to the 0 vector. Okay, so if we want to find where the gradient of f equals 0, we first need to find the gradient of f. So let's calculate the gradient of f by taking the partial derivatives of this function. So if we take the partial derivative with respect to x, we get negative 3x squared plus 4y. And if we take the partial derivative of the function with respect to y, we would get 4x minus 4y. Okay, we get critical points when this is equal to the 0 vector. That gives us a system of equations. We want the first component, negative 3x squared plus 4y, we want that to be 0. And we want the second component, 4x minus 4y, to be 0. We want both of these to be 0 at the same time, so we need to solve the system of equations. All right? There are multiple ways to solve a system of equations like this. Generally, you have to be careful with using elimination for a system like this. Elimination works great for linear systems. This is a nonlinear system because one of the variables is squared. Elimination can sometimes be helpful, but a lot of times the better option is substitution. Okay? For this particular problem, elimination would actually be a good approach because 4y and negative 4y could cancel if I add the two equations together. Your goal is to take your system with however many equations, however many variables it has, and reduce the number of equations and number of variables gradually. In this case, I have 2 equations and 2 variables. I want to reduce it to 1 equation with 1 variable. All right. While we can use elimination here, I'm actually going to use substitution just so you can see it. I'm going to take the second equation because it's going to be a little bit easier to isolate one of the variables here. I have 4x minus 4y equals 0. And I'm going to express one of the variables in terms of the other. If I add the 4y to the other side, if I divide both sides by 4, I find that in order to have a critical point, I need x to be equal to y. All right? So now I'm going to take that and I'm going to plug it in here. So I could either plug in x for y or y for x. Okay? In this case, I will plug in x for y. So I get negative 3x squared plus 4x equals 0, plugging in x for the y here. All right? So let's solve the system. I can, with a system like this, or with an equation like this, with a higher power, we want 0 on one side. That's what we got, which is good. And then I could try to solve by something like factoring, or since it's quadratic, if all else fails, I could use the quadratic formula. Factoring, though, is going to work here, and that's going to be the option we want. So let's factor out an x. Leaves me with negative 3x plus 4. Now I have 2 things that are being multiplied together that equal 0, which means one of those 2 things has to be 0. If you have 2 things that multiply together to give you 0, one of the 2 things has to be 0. So one way that could happen is if the first factor there is 0, which gives us x equals 0. Or the other option is the second factor is 0. So that would be negative 3x plus 4 equals 0. And if I solve for x, I get x is equal to 4/3. Okay? So that tells me the x values of that solve the system of equations. I need the xy pairs, though, right? So for that, I'm going to go back to my substitution. I know x and y have to be equal for any point that makes this system of equations true. So my critical points here, the points that solve this system, that make the gradient equal to 0, are going to be when x is 0, and according to this, since y has to be x, y also has to be 0. So one of the critical points is 0, 0. And then the other critical point I get when x is 4/3 and y is 4/3. And those are my two critical points for this particular function. If we want to find local maxima and local minima, this is where we look. So great, we have identified the critical points to this particular function. We know if there are local minima or local maxima, they have to occur at these points. But how do I determine if there's a local minimum or a local maximum or something else here or here? So in order to do this, we are going to use the second derivative test for two variable functions. So I'm going to first state the test, and then we'll try to understand it. So the second derivative test for two variable functions. Okay, so let's let z equals f of xy be a two variable function. With continuous first and second order partial derivatives. Around some point, let's be a little clear. In the neighborhood of x naught, y naught. Okay, so this is just the bookkeeping. We have some function, it's a two variable function. Its first and second order partial derivatives are all continuous. First off, it's differentiable, so you can find those partial derivatives, and then once you find them, they're continuous. Now, they don't have to be continuous everywhere. They do have to be continuous in the neighborhood of the point we're interested in. Okay, so the neighborhood means just somewhere around it. Doesn't have to be very big, but in some small region around this point, it's continuous. Okay, so we're going to assume this is a critical point so that the gradient of f is 0. Suppose that the gradient of f at this particular point, x naught, y naught, is equal to the 0 vector, which makes this a critical point of f, right? So now let d equal to the product of the second order partial derivatives, fxx and fyy, at the point. And then I'm going to subtract the second order mixed partial derivative squared. This quantity is going to be the key to determine if we have a local maximum, if we have a local minimum, or something else. Okay? Let me just bullet point it. If d is positive, if it is a positive quantity, then x naught, y naught is a local extremum. Okay, it's either a local maximum or it's a local minimum. Actually, finding out which it is easy once you identify that it is a local extremum, and we'll discuss that. Okay, but if d is positive, that means we either have a local maximum or a local minimum at the point. We have a local extremum. If d is negative, then the point is a saddle point, which means it wouldn't be either a local extreme, local maximum, or a local minimum. It's something else. And there is one other option. We've considered d being greater than 0. We've considered d being less than 0. If d is exactly equal to 0, then what happens? Well, if d is exactly equal to 0, then the test is inconclusive. And you would have to use more creative means specific to the problem to try to identify if you have a local maximum or a local minimum. We really won't be dealing with this situation in this class. Just be aware that it is a possibility. Okay? Okay, so proving this and really understanding the details of this is beyond us in this class. It goes outside of what we are able to do. But we can try to get some sense of why it works. Okay? Why is it that if d is greater than 0, then we have a local extremum, either a local maximum or a local minimum? So to best understand this, it's easiest to think about the case when this mixed order partial has gone away. So imagine that's not there. Okay? Just focus on the product of these second order partial derivatives. Now, these are not mixed partial derivatives, so they are telling us about the concavity. This tells us about the concavity of f in the direction of x. This tells us about the concavity of f in the direction of y. Okay? Now, if this is gone, the only way d could be positive is if both of these are the same sign, right? Either both of these are positive numbers, and when we multiply them together, we still have a positive, or both of them are negative, and when we multiply them together, they turn positive, right? So the idea here is that the concavity in the direction of y and the concavity in the direction of x agree, right? Either they're both negative and we have a local maximum, or maybe they're both positive and we have a local minimum. Okay? So that's what's going on here. If both of these are either both concave up or both concave down, then when we multiply them, because they have the same sign, we'll get a positive number. Okay? And that could indicate we have a local maximum or local minimum. Now, what about this d being negative case? So again, imagine that's not there. That really complicates the understanding, though it is necessary, and I'll show you why eventually. Okay? But if d is negative, that and we only have these two terms, then these need to be opposite signs, right? One would be concave up and the other concave down, or the other way around, right? Because they have to have opposite signs. Only two numbers with opposite signs, when you multiply them, would you get a negative number. Okay? So that means in one direction, we'd be concave up. In the other direction, concave down. And we get something like a saddle. Let's see if I can draw it. Okay, something like that. And so the point here would be neither a local maximum or a local minimum. In the different directions, you get different values. So I do have an image of that here just for reference. Okay, so here we have a saddle. With x fixed in the y direction, we're concave up, right? At the origin, we're concave up. The origin is a critical point in this for this function. And at the origin, we're concave up in the y direction, but in the x direction with y held fixed, we're concave down. And if we multiply those two concavities together, concave up would give us a positive second derivative, concave down a negative second derivative. You multiply them together, you get a negative number overall. Okay? And then if d equals 0, then the test is inconclusive. Okay? And we have something more exotic happening. What about this second term here? Why is that even necessary if this is telling us everything we need to know? Well, it turns out looking in just the x direction and just the y direction isn't quite enough. Okay, so let me give you an example. Here's an interesting looking surface. It is a saddle, isn't it? We could see it's a saddle. At the origin, that's a saddle point. If we look at the trace in the y direction, holding x fixed, notice that we are concave up, right? And if we look at the trace in the x direction, holding y fixed, we are also concave up. So in both directions, we're concave up. So if all we're looking at is the concavity in the x direction, the concavity in the y direction, then they're both concave up, and we would get we'd get d greater than 0, right? But we need to take into account the extra twist that could happen. Remember, this mixed partial derivative tells us information about the twist. So by including this, we would be able to show, oh, no, in fact, that would be a saddle point. Okay, so this is our second derivative test. This is the test we are going to use to identify whether critical points are a local extremum or a saddle point. By the way, once we identify it's a local extremum, whether it's concave up or concave down, then we just have to look at one of the two twice partial derivatives, right? The second partial derivative with respect to x or the second partial derivative with respect to y. We know that they will have the same sign. So once we know we have a local maximum or a local minimum, if, say, in the x direction, we have a local maximum and we have a positive second derivative, that would mean that we have a local minimum there. Okay, so once we know we have one, we only have to look in one direction to identify whether it's a local max or a local min. So let's go back to our previous example, the one where we already found the critical points, and let's identify whether we're dealing with saddle points or local extrema using the second derivative test. Okay, so in order to apply the second derivative test, I need to calculate d, which we call the discriminant. So I need my second partial derivative with respect to x, second partial derivative with respect to y, and then I'm going to subtract my mixed second partials squared. Okay? So just as a reminder, let's just carry down our first order derivatives. So our first order derivative with respect to x is negative 3x squared plus 4y. Negative 3x squared plus 4y. And then our first order derivative with respect to y is the second component of our gradient. That was 4x minus 4y. Okay? And now we just need our second order derivatives, right? So I'm going to take the second derivative with respect to x. So I'm going to take the derivative of this function with respect to x. I just get negative 6x. I'm going to take the second order derivative with respect to y. So this function with respect to y, and I get just negative 4. And then I also need my mixed partials. So fxy. Now, we know that this is the same as fyx, right? We know that mixed order partials, the order doesn't matter. So that means I could either take the derivative of this function with respect to y or this function with respect to x. Doesn't matter. Sometimes one will seem to be a little easier than the other one. In this case, they're about the same. I'll take the second derivative of this function with respect to x. So if I take the derivative of this function with respect to x, I just get positive 4. Okay? So if I plug these into my discriminant, then I get generally negative 6x. And then my second derivative with respect to y is negative 4 minus my second order mixed partial derivative. And so that's going to be 4 squared. So I get 24x minus 16. Now what I want to do is I want to evaluate that at each critical point. Okay, let's start with 0, 0. So I'm going to bring that down here. Let's evaluate our discriminant at 0, 0. So I have 24x minus 16. So I'm going to plug that in. 24 times 0 for the x minus 16. I get negative 16. Okay, that is a negative number. When our discriminant is negative, that means we have a saddle point. So we can conclude that the origin 0, 0 is a saddle point, neither a maximum or a minimum. Okay, now let's find our critical point 4/3, 4/3. Let's see if that is a saddle point or a local max or a local min. Okay, so D 4/3, 4/3 is going to be, so I get 24 times x minus 16. 24 times 4/3 is, well, let's see, 3 goes into 24, 8 times 4 is 32, minus 16. I'll get positive 16. Okay, positive 16 is a positive number. When my discriminant is positive, then I have a local extremum. So I'm going to have either a local max or a local min at 4/3, 4/3 is a local extremum. To determine whether it is a local maximum or a local minimum, I need to look at the second order partial for either the x direction or the y direction. It doesn't matter. They are guaranteed to match. They will both have the same sign. In this case, this one looks a little bit easier because I don't have to plug anything in, right? Since the second order partial in the y direction, so you don't want to look at your mixed order. You only want to look at either this one or this one because it will tell you the concavity. Okay? So I'm looking at the second order partial in the y direction. I know when I plug in the point, I get negative 4. It's always negative 4. Okay? That means a negative second derivative means concave down, right? So in the y direction, it's concave down. And if I have a local extremum, the only way I'm concave down is if I have a local max, right? We must have a local maximum at the point. Okay, so we have identified both our critical points, and now we have categorized both of them. We know that 0, 0 is a saddle point. It's neither a local maximum or a local minimum, but 4/3, 4/3 is a local extremum. It is the only local extremum on this function, okay? And it's a local max. So let's graph this. Let's confirm what we have here. Let me pull over our graphing calculator here. Let's start by plugging in our function. Okay, so we have f of xy equals negative x cubed plus 4xy minus 2y 4xy minus 2y squared plus 1. Okay, so let's see what we got so far. So that's what we're dealing with. And right away, it looks like we have the correct idea, doesn't it? You can see there's a saddle point right there. It looks like it's at xy equals 0, 0. And then we do have a local maximum on the top of this hill here. Okay, so let's plot the points. Let's make sure that we actually have it. So our saddle point should have been at the point 0, 0. Helps if I actually plug in the point. There we go. And indeed, that is exactly where we expected the saddle point to be. And then we found a local maximum when x and y are 4/3. And there's our local maximum right at the top of that little hill. There's one other topic we need to discuss before we finish this section. We need to talk about finding absolute extrema for a continuous function on a closed and bounded domain. So for this, we're going to use a really important theorem that you've probably learned in single variable calculus and have probably forgotten, the extreme value theorem. And it states in summary, if a function is continuous on a closed and bounded domain, then it has an absolute maximum and an absolute minimum on that domain. Okay, what the heck does that mean? So its function, it's continuous, so no breaks, no rips, no tears, no holes. And it's continuous on a closed and bounded domain. So bounded means it can't go on forever to infinity. Okay? We're only looking in a fixed region, a bounded region. And it is closed, which means that boundary is included in the space that we are looking at. Okay? Now, if those conditions are met, then for sure, guaranteed, it has an absolute maximum and an absolute minimum somewhere on that domain. This is true for the single variable case, and it's true for the multivariable case. Let's look at the single variable case. So if we have some function in the single variable case, now we're going to restrict ourselves to a bounded domain. So we're not just going to shoot off to the positive x direction forever or the negative x direction forever. We're going to limit ourselves between two values. We're going to bound ourselves. Okay? If we have some continuous function in between them, then for sure we have an absolute maximum and an absolute minimum somewhere on that closed and bounded domain. Okay? Notice a few things. The closed part means that the dots, the endpoints here, are included in the domain. These aren't open circles, right? These are closed circles. We are including the endpoints. That's the closed part of the closed and bounded. Also, notice that the endpoints themselves could be the absolute maximum or the absolute minimum. In this particular example that I've drawn, the dot is the absolute minimum. This left endpoint is the absolute minimum. Okay? There is no way to connect this dot to this dot in a continuous way without having an absolute maximum and an absolute minimum. Okay, there are ways where you wouldn't be continuous, where you wouldn't have an absolute maximum or an absolute minimum, right? You could have an asymptote. Actually, that's not a good example. You could have a hole. Okay, there's no absolute maximum here, right? The absolute maximum would be here, but there's not a point there. It's a hole. But that doesn't violate this theorem because it's not continuous. Okay. The same holds in the multivariable case. Now, rather than making you suffer with my terrible drawings, let me hold this example here. So I have a paraboloid here. Now what we're going to do is we are going to restrict our domain to only a circle. Right now this paraboloid, the edge here on top, it's false. If I zoom out, it keeps on going, right? It's just that's where the graphing ends. But what we're going to do is we are going to restrict this paraboloid to within a circle in the xy plane. Okay, so within a circle in the xy plane. So let me put the restriction on. Okay, see the restriction now. If I look in the xy plane, we do have a circle. It's of radius equal to the square root of 2, and we're looking inside the circle. Notice that the function is continuous, right? There are no breaks, rips, tears, holes, nothing like that. It is closed and bounded. Certainly bounded, right? It doesn't shoot off to infinity in the x direction or the y direction or any direction. And it's closed, meaning we are including the boundary as part of the domain. So if we do all that, notice we are guaranteed to have an absolute maximum and absolute minimum. The absolute minimum is the vertex of the paraboloid, right? And the absolute maximum is on the boundary. On the boundary. This edge up here is the absolute maximum. And so when we are looking for these absolute extrema, we need to make sure that we check the interior of the domain, but also we need to be very careful to check the boundary of the domain separately. Okay? So let's take a look at an example. So we want to find the absolute maximum and minimum values of the function x squared plus 2y squared over the circular region x squared plus y squared is less than or equal to 4. Okay? So the values that we are allowed to plug into the function, the region we are looking at, if we just look at the xy plane and look at the xy values we're allowed to plug in, we're only allowed to plug in the x and y values within a circle of radius 2. Okay? So something like this. Those are the x and y values that we are allowed to plug in. Now notice this is a closed and bounded domain, so we are guaranteed to have an absolute maximum value, and we are guaranteed to have an absolute minimum value so long as the function is continuous. And this function is continuous. It's just a polynomial of 2 variables. We don't get any division by 0 or negatives under square roots or anything like that, right? Okay, so to proceed, we need to check 2 places. We need to check the interior of the circle, and then we need to check along the boundary. So we're going to do the interior first. To check the interior, we just want to find any critical points in that interior region, and we want to find them the way we normally do. Any point where the gradient is equal to 0. Okay? The gradient is equal to 0 in that interior region. That means it has a horizontal tangent plane, and so it might be the bottom of a local minimum and the top of a local maximum. And a local minimum and a local maximum would be a good place to check for an absolute maximum or an absolute minimum, right? So let's take the gradient of f, and then we'll set the gradient equal to 0 and solve. All right, so gradient of f, we have x squared plus 2y squared. If I take the derivative with respect to x, that's just 2x. With respect to y, that's just 4y. If I set that equal to the 0 vector, then I would get both of those equal to 0, when 2x equals 0 and 4y equals 0. That gives us a very easy system of equations to solve. You can see right away that the only place that that is going to happen is when x and y are both equal to 0. Okay, so that is one of our critical points, and it's a good idea to construct a list of critical points. So let me do that over here. Points that we want to check. All right. Now, you do need to make sure that any critical points you get here are actually in the interior. Sometimes you'll do this process and you'll get a critical point somewhere outside of our region. If that happens, we don't care because it is outside of the region where we are looking. This particular point is inside of our region, and so we do want to check it. Okay? Now, I don't need to do a second derivative test or anything like that here because we are looking for absolute maxima and absolute minima. Okay? It's actually going to be really easy to check for those because we're going to find only a few critical points, and if we plug them back into the function, we just need to check which one's the biggest and which one's the smallest. Since we know we have an absolute max and an absolute min, we know that whichever point gives us the biggest value, that will be our absolute max. Whichever point gives us our smallest value will be our absolute min. Okay? So we won't worry about whether this is min or max until we get all the critical points. All right? So we're done with the interior. Now we need to look at the boundary. Now to consider the boundary, what we want to do is we want to parameterize the boundary. We want to find a vector-valued function that traces out the boundary. In this case, our boundary is just a circle. That's easy to trace out. The easiest way to trace out a circle is to use r cosine t, r sine t, where r is the radius of the circle. This particular circle is a circle of radius 2, right? So my r will be radius 2. And if I want to go all the way around the circle, like I do in this case, then I want to make sure t goes from 0 to 2 pi. Right? And since it connects up nice and smooth, that's all we're going to have to do. We're just going to have to look at this boundary. So what we want to do now is we want to see what function f does as we move along that boundary. So we are going to plug in our parameterization of that boundary into function f. Parameterization of the boundary into function f. So function f is x squared plus 2y squared. So that's x squared plus 2y squared. And I just plugged in the x component of my parameterization and the y component of my parameterization. And now all this is doing is we're looking at just the function value, but just as we go along the boundary. So we're focusing on the boundary. That's all we're doing is we're traversing the boundary and seeing what the function value is along it. Okay? Now I could tidy this up a little bit. If I square, I get 4 cosine squared t, and then 2 sine t. If I square that, I get 4 sine squared t times another 2. That'll be 8 sine squared t. And I've got a cosine squared plus a sine squared. I know cosine squared plus sine squared is 1. Now this isn't quite that. This is 4 cosine squared plus 8 sine squared. But what I could do here to tidy it up a little bit more is I could break up the 8 sine squared into a 4 sine squared plus another 4 sine squared. And now if I factor out the 4 here, I'll get 4 times cosine squared plus sine squared. Cosine squared plus sine squared is 1. So this will just simplify to the 4 I pulled out times 1. So that's 4 plus 4 sine squared t. Okay? Now what we want to do is we want to take the derivative of this. If we take the derivative of this, we'll be able to find out where along the boundary we are reaching local maximums, where along the boundary we're reaching local minimums. Okay, now all we're doing is moving along the boundary, so it's only a local max or local min relative to the other points on the boundary. But that's enough. We just need places to look. We need to limit ourselves from looking at all of that circle to see if we have local min and absolute minima and absolute maxima, to looking at just a few important points on the circle where it could be. Okay, so we're going to take the derivative. Derivative of 4 is 0. Derivative of 4 sine squared t will be 8 sine t cosine t, using a little chain rule there. And I'm going to set that equal to 0. Okay, I'll get critical points along the boundary when my derivative along the boundary is equal to 0. So 8 sine t cosine t equals 0. I'm multiplying these together, which means the only way I can multiply things to get 0 is if one of these things is 0. Now, the 8 can't be a 0, so that's ruled out. So either the sine of t has to be 0, okay? And that's going to happen at t equals 0 and t equals pi. Or cosine t is going to be 0. And that's going to happen in our region from 0 to 2 pi. That happens at pi over 2 and 3 pi over 2. And with that, we've looked all the way around the circle and we found all the critical points. Okay? Now what we want to do is we want to translate these into actual points. So we're going to plug them back into r of t. And that will tell us the actual xy points that we have those critical points along the circle. Okay? So I'm going to do r of 0 first. And it was 2 cosine t, comma 2 sine t was my parameterization. So I'll just plug in the 0 for t, and I get 2, 0. So that's going to be another critical point that I'm going to add to my list up here. Another place I need to check. Okay, and I do that for each value. So I did it for the 0, now for pi. So r of pi, I get 2 cosine of pi, 2 sine of pi. That will be negative 2, 0. I'll add that to my list too. I'll do that in a moment. Let's finish off plugging these in first. R of pi over 2, we get 2 cosine pi over 2, 2 sine pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So 1 times the 2 that's already there is 2. And then just one more value of t to plug in, 3 pi over 2. 2 cosine 3 pi over 2, comma 2 sine 3 pi over 2. Taking the, not taking the derivative, just evaluating. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. So I'm going to get 0, negative 2 once I complete the calculation. So I want to make sure all of these are added to my list of points. So I already got 2, 0. Wanted also negative 2, 0, 0, 2, and 0, negative 2. Okay? Now, one of these must be the location of the absolute maximum, and one of these must be the location of the absolute minimum. Since we know one of these is the location of the absolute max and one of them is the location of the absolute min, all I'm going to do is I'm going to plug them into the original function and find where I get the highest value and which one gives me the lowest value. So I can find the absolute max and absolute minimum. I don't need to do a second derivative test if I'm looking for absolute extrema on a bounded domain. Okay, so now let's just plug in. I've got my critical points. Let's plug them into f of xy equals x squared plus 2y squared. So if I plug 0, 0 in, I'm going to get 0. If I plug 2, 0 in, I get 4. If I plug negative 2, 0 in, I also get 4. If I plug 0, 2 into the function, I get 8. And 0, negative 2 into the function, I also get 8. Which means this value right here, that's the smallest value, that's 0. That's my absolute minimum. And these values right here, they're both the largest value that I get, so they both must be the absolute maximum. All right, so I could summarize my results like this. F of xy has an absolute minimum of 0 at xy equals 0, 0. Notice there's a difference between what the absolute minimum is and where it is. The absolute minimum is the function value. This was the absolute minimum, but the absolute minimum was at the point 0, 0. That's the point I had to plug in to reach that absolute minimum. Similarly, f of xy has an absolute maximum of 8, and it's at 2 different points. They were at the points, let's check. 0, 2, and 0, negative 2. So it reaches that absolute minimum at 2 different places. Okay? All right, so we have the points. Let's see how this translates to the graph. Right? So this is the function restricted to the circle. Here, if I look down the z-axis, you can see I really am restricted to the circle x squared plus y squared is less than or equal to 4. Okay, so if I restrict the surface to the circle, that's what I get. So what were the points that we found? We found the absolute minimum was at 0, x and y equals 0, 0, and the absolute minimum was 0. Okay, so let me zoom in just so you could see. Actually, you know what? Let me just make the point bigger. Nice and big. I don't think that purple color shows up very well. Let's make it red. Okay. A little too big, I think. Okay, but you can see that that is definitely the absolute minimum, right? Our absolute maximum was 8, and it occurred at 2 points. It occurred at 0, 2. So 0, 2, 8, and 0, 2, negative 8. Let's make these blue. I'm sorry, put the negative on the wrong value. 0, negative 2, positive 8. That's better. Okay, so you can see that really is the absolute maximum of this surface. Okay, and then the other 2 critical points we got were 2, 0, 4 and negative 2, 0, 4. Okay, and so you could see why we got them as critical points, can't you? Along the boundary, they are local minima. And so you could see why we had to consider them. But they are neither the absolute lowest point nor the absolute highest point. Okay? Let's do one more example. We want to find the absolute extrema of the function xy minus x minus 3y over the triangular region with vertices 0, 0, 0, 4, and 5, 0. So we again want to find the absolute maximum and absolute minimum. Absolute extrema is just a word saying both the absolute extreme values. The absolute maximum, the absolute minimum, right? So we want to be over the triangular region. So let's kind of draw out our region. Always a good strategy when dealing with these maximization, minimization problems of over a bounded region to first draw the region. Okay, we want a triangular region with vertices 0, 0. So right there, 0, 4. So we'd go up 4 units. Right there. And 5, 0. So we'd go over 5 units. 2, 3, 4, 5. Okay. So our triangular region is this region right here. This is where we want to look for our absolute extrema. This is where we care. All right. So just as before, we're going to look in two places. We're going to look in the interior and then along the boundary. So let's start with the interior. And with the interior, I'm looking at the whole surface. So I'm going to find the critical points as I normally do. I want to take the gradient of the function and set it equal to the 0 vector and solve. Okay. So the gradient of f with respect to variable x, I get y minus 1. And the derivative of f with respect to variable y, I get x minus 3. So I'm going to again set that equal to 0 to find my critical points. That gives me a system of equations. I want y equals 0 and x minus 3 equals 0. Again, these are two very, this is a very simple system of equations. We can see very quickly that we have a critical point at 3, 1. So the very first thing we need to do is check, is this point actually in our region? Okay, so we want to be at 3, 1. So if you've drawn your picture well enough, you can find that 3, 1 is right there. It does look like it is in the region, doesn't it? Okay, so that will be one that we want to check. So our list of critical points for this region is 3, 1 so far. That's what we get from the interior. Again, if this point was outside of the boundary, if it was up here somewhere, then we would not include it. We only care about maximum and minimum values in this region. You have a point outside that region, we don't care about it, you just ignore it. Okay? So we've done the interior, now we need to look at the boundary. Now the boundary is going to be tricky. I want to find a way to parameterize the boundary, but how do I parameterize a triangle? We have a way to do that? So the trick with something like this is to break it into pieces. I'm not going to parameterize the whole boundary at once. I'm going to look at one side at a time. So I could look at this side and then separately parameterize this side and then separately parameterize this side. By doing all three sides separately, it makes it a lot easier. Okay? It's a fair bit of work, but it is easier. So let's label our sides. So let's say side 1, side 2, side 3. Okay? So for side 1, it's just a line going from one point to another point. We're very good at finding the equations of lines, right? The equation of a line is just a point on the line. I can use 0, 0, plus t times a vector in the direction of the line. If I'm going from 0, 0 to the point 0, 4, then this vector, this direction vector, is the vector 0, 4. End minus start. I want to end there. I want to start there. If you subtract the points, you get the vector you want. Okay? So this will be the boundary for that first side. So I'll call it R sub 1, 1 for the first side. And now I want to be very careful here. I want to make sure I know what t's I want to use. All right. Now, if you've set up your line correctly, usually you can set it up so your t goes from 0 to 1. But you should always check. It's very easy to get it wrong. So make sure that when you plug in 0, you should get your first point. When you plug in 1, you get your second point. Okay. So if I plug in 0 for t, I'll just get 0, 0. That's there. That's where I wanted to start. That's good. If I plug in 1, I get 1 times 0, 4 plus 0, 0. That's 0, 4. That's the point I wanted to end at. And so I do the whole side. Okay? Now what we want to do is we want to plug this in to our function. And that allows us to focus on what the function is doing along that edge, along that first side. Okay? And maybe actually, before I do that, let me write this as a single vector rather than a sum. I get 0, 4t. That'll make it a little bit easier to plug in. So my function was, what was it? xy minus x minus 3y. So in place of x, I'll plug in 0. In place of y, I plug in 4t. So x, y minus x minus 3y. Most of this just goes away. I'll just be left with negative 12t. I want to take the derivative of this to figure out any local maxima or minima along this curve. So take the derivative. Derivative of negative 12t is just negative 12. You could try to set that equal to 0, but it has no solutions, right? So we set our derivative equal to 0, but there's no solutions, which means we don't get any critical points along that side. We don't add any critical points to our list by looking at that first side. Okay, so that's side 1. Do it up here, actually. Side 1. Now let's do side 2. So again, we need a parameterization for that side. Okay, we again recognize that we're dealing with a line here. And so we can use our formula for a line. So my parameterization for my second side, I'm going to take a point on the line. I can choose 0, 0, which is probably the easiest, right? If I'm looking at this line, let me scale up the size a little bit. Okay. I want to start at 0, 0. So that's probably the easiest point. And I want to end at 5, 0. So the direction vector, if I take the endpoint 5, 0, subtract the starting point 0, 0, the direction vector is 5, 0. So 0, 0 plus t times my direction vector 5, 0. And again, you need to make sure you know what t's work. Okay, because this line, it really extends past the edge, right? It's really this whole line, but we only care about this portion of the line. So we need to make sure we know what t's we're interested in, what region of the line we're interested in, because if we get a critical point somewhere over here, we know, nope, we don't care about that. Okay? So we need to be careful. Now this one goes again from 0 to 1, but always check. If you plug in 0, do you start where you think you do? If I plug in 0, I start with 0, 0. That's where I wanted to start. If I plug in 1 and do the vector arithmetic, if I plug in 1, I get 1 times 5, 0, plus 0, 0. That's the point 5, 0. That's where I wanted to end up. So yes, this is the range of values of t that I want. If I do the vector addition, I get 5t comma 0. Okay, now let's plug that into our function f. That will tell us the function value along that bottom side. Okay, so again, function f was xy minus x minus 3y. I'm going to plug in 5t for x, 0 for the y. So x times y minus x minus 3 times y. Okay, again, we get a lot that goes to 0. That goes to 0, that goes to 0. I just get negative 5t. To find my critical points, I want to take the derivative along this boundary, this side, and then set that derivative equal to 0. So derivative with respect to t, that'll tell me how function f is changing along this boundary. Just negative 5. If I set that equal to 0, we can see very quickly that also has no solution. Okay? All right, we have one more side to check. One more side to check. That's side 3 here. Okay? So let's check side 3. Again, I need a parameterization for that side. All right, it's again a line. So I need a point to start with and a point to end with. Let's start with this point. That's the point 0, 4, and let's end at 5, 0. Okay, so I'll start at 0, 4. So that's the point I'll use in my parameterization, 0, 4, plus t times the direction vector. So if I want to end at 5, 0, I want to start at 0, 4. 5, 0 minus 0, 4 will be 5, negative 4. That's my direction vector. And minus start. So my parameterization is the starting point, 0, 4, plus t times my direction vector, which we calculated was 5, negative 4. And I just found that direction vector by taking the point I want to end at, subtracting the point I started at. Okay? Now let's make sure that the t ranges from where we think it does. So if I plug in 0 for t, that would just go away. I just have 0, 4. That is the point I wanted to start with. So that's good. Okay. And then make sure that when I plug in 1, that's the point I want to end at. So if I plug in 1, I get 0, 4 plus 1 times 5, negative 4. 0, 4 plus 5, negative 4. The 4s would cancel in the second component, and I'd get 5 in the first component. So I get 5, 0. So that also checks out. That's the point I wanted to end at. Okay. So this does trace out the line I want, and this is the range I want t to be in. Okay, so I'm going to plug this into my function. Oh, let's simplify my function here first. So I get 0 plus 5t in the first component and 4 plus negative 4t in the second component. Okay, so that'll be the x and y I plug in. So f of r3t, so that I can look at the function value along that third side. The function again is xy minus x minus 3y. So I'm going to plug in 5t for x, 4 minus 4t for y. So x times y minus x minus 3 times y. Let me just double check I remembered everything correctly. Yeah, we're good. Okay. I just plugged into the function x, y minus x minus 3y. Okay, let's tidy this up, and then we'll want to take the derivative to find our critical points. So here I need to distribute. I get 20t minus 20t squared. Here I get negative 5t. And here, distribute again, I get negative 12 plus 12t. Let's combine my like terms. I only have the one t squared term, so I'll put that in front. Negative 20t squared. Then my t's, 20t minus 5t plus 12t. That's what, 27t? And then I have just one term without a t, so minus 12. Okay? Now take the derivative. So derivative of f of r3t, I get negative 40t plus 27. I want to set that equal to 0. This equation does have a solution, right? So let's solve it. The t I get is subtract the 27 and divide by the negative 40. The negatives cancel. I get 27 over 40. And unfortunately, there's no way to simplify that. Double check that it is in our range, right? And it is. It is between 0 and 1. So we do have a legitimate critical point here. Now, this is the t value of the critical point. We need to plug it back into our parameterization to find the actual point value. Okay? So R3 of 27/40ths, I'm going to get, scroll up just a hair. Here's my R3 function, so I want to plug into this. So I get 5t, so 5 times 27/40ths for my first component. And for my second component, that's 4 minus 4t. Five goes into 40 8 times, 4 goes into 40 10 times. So I get, for my first component, 27/8. For my second component, that's 4 minus 27/10. And then finally, I want to subtract these by getting a common denominator. 4 is the same as 40 over 10. So that will give me a common denominator of 10. So I can subtract those. And I get 27/8, comma, 40/10 minus 27/10, that's 13/10. So that's another critical point. Wait, what was it again? 27/8, 13/10. 27/8, 13/10. So we've checked all three sides. Does that mean we have all critical points? So because we split it up, there are actually 3 other critical points we must check. Just like when we are looking at a single variable function and looking for the absolute maximum and minima, we always have to include the endpoints, right? The boundaries. Well, by restricting ourselves to one side, at a time, each one of those sides has some boundary points. The derivative here, each one of these derivatives, does not tell us information about those boundary points. In order for a derivative to make sense, you have to be able to approach it from both sides. But if we're stopping at this edge and this edge, there's no other side I can approach from. Right? So you always, always, always include any sharp points along your boundary in your critical points list. Okay? So that means I need to include this point, and this point in my list of critical points. You always include sharp points in your critical point list because they will always represent a place where you transition from describing a side one way use a different color, describing this side one way, and then we describe this side a different way. And this was an edge point in both cases. And so the derivative in either case tells us nothing about whether that point is a local max or local min. Okay, so we also want to include 0, 0, that point. We want to include 0, 4, that point. And we want to include 5, 0, that point. So if you have any sharp points, you want to include them, right? So if we have an, we do have an absolute maximum and an absolute minimum. We know that the absolute maximum and absolute minimum will be at one of these 5 points. So all we have to do now is plug in and see which gives us the biggest value, which gives us the smallest value. Okay, so our function is f of xy equals xy minus x minus 3y. And especially for this one, this looks like it might be a calculator problem, right? So let me pull up my calculator. Here we go. I'll just plug in f of xy equals xy minus x minus 3y. And now all I have to do to calculate the function value for those critical points is f of 3, 1 gives me -3. Okay, so I type in the function first, makes it real easy to calculate the function values for everything else. So f of 3, 1 is -3, f of, now the nasty one, 27/8, comma, 13/10. It's -2.8875. F of 0, 0 is 0. F of 0, 4 is -12. And f of 5, 0 is -5. Okay, so let me transfer those to our work right here. So 3, 1, that was -3, -2.8875, 0, -12, -5. Okay, which means the largest value among these is actually the 0, right? So that will be our absolute maximum. And the smallest value is the -12. That's the absolute minimum. So it's really good that we included those 3 corner points, right? Because it turned out both the absolute maximum and the absolute minimum were at those corners. So if you don't include them, you might miss something, right? So let's summarize. Let's write our answer. F of xy has an absolute minimum of -12 at xy equals, and what was it? So the absolute minimum was at 0, 4. The absolute maximum was 0 at 0, 0. Zero, 4. F of xy has an absolute maximum of 0 at xy equals 0, 0. So these are the absolute maximum and absolute minimum values of function f and where they are on the domain that we were restricted to. Okay? So let's confirm this now by taking it to a 3D graphing calculator. Here's the function we're looking at. Okay, let me zoom out just a little bit so we could see the whole surface. Okay, so there's our surface. We are restricted to that triangle. Okay. In the xy plane, we are restricted to that triangle. Okay, so where were our critical points? So first, our absolute maximum was at 0, 0. There we go. I'll make that red. And so you can see, yep, that is definitely where the absolute maximum is, right? The absolute minimum was at 0, 4, f of 0, 4. There's the absolute minimum. Okay. Now, what about those other critical points? What did we have? We had, let's check. We had 3, 1, and we had 5, 0. 3, let's do 5, 0 first. Okay. So there's, it's a little interesting at 5, 0. But really the only reason we included is because we couldn't find information about it any other way. It was a point that right at the corner, and so we couldn't use a derivative to find any information about it. Okay, in this case, it's kind of a local minimum, right? It's not an absolute minimum. And there was 3, 1. So you can see here, let me hide everything but the point I'm talking about. You can see that it's not at the edge, it is in the interior, and it looks like a saddle point, doesn't it? Okay. And then our last point, what was it? It was 27/8, 13/10. 27/8, 13/10. And it is right on the boundary, and you can see that along the boundary, it is a local maximum, even though it is neither an absolute maximum or a local maximum, or an absolute minimum, rather, on the surface as a whole. So we were right to include it as a critical point, but it ended up being neither our absolute maximum or absolute minimum. Okay?